So first of all, thank you all for coming. I really appreciate your ditching the ML and data science stuff to come here for random puzzles. I hope it'll be worth your while. Yeah, I guess most of you probably have had some exposure to Python. This is not going to be a lot about Python. I just cheated and put the word in the title in the hope of attracting people. This is really going to be about a few puzzles that we'll talk about, and hopefully you have creative ideas of, how you can maybe implement them. You don't have to use Python. You can use your favorite platform or programming language. I do realize this is like the post-lunch session, so I plan to keep it light, or at least let's start light with this was inspired after all the wonderful performances last evening. So I thought we'll start with a Bollywood theme, and let's start with these ladies and gentlemen here. Some of you may be too young to recognize some of their faces, but hopefully not. What we're going to do is build a graph. So how many of you are familiar with graphs, as in not plots, but just networks, like graphs made out of networks? Like the Facebook graph, does that make sense? Every person is represented as a node, and if two people are friends, then there's an edge that goes between them. So you probably call them networks. Some people like to call them graphs, which is very confusing because graphs is like a terribly overloaded word. But yeah, so we have vertices or nodes or whatever you want to call them corresponding to these actors. And when do you think we want to draw an edge between two actors? Yeah, any common relation, like if they've been involved in a scandal together, if they've done a song together, if they've done a movie together. So let's pick something respectful because this is being recorded. Like, so let's say that if two people have done a movie together, then we draw an edge between them. So this is more of an age test than anything else. But do you think Shah Rukh and Deepika have worked together? And if yes, just give me a name of a movie that they've worked together in. Okay, Om Shanti Om. Perfect. Yeah. What about Shah Rukh and Juhi? Acha, theek hai, arey waah. They've clearly done a lot of movies together. So Dar, Bhootnath, Fir Bhi Dil Hai Hindustani, and I think something else also. Yes, boss. Yeah, okay, very nice. What about Shah Rukh and Katrina? Wow, Jab Tak Hai Jaan. Theek hai, perfect. What about Shah Rukh and Amitabh ji? Mohabbat hai. Theek hai. What about Shah Rukh and Rishi Kapoor? Does anybody? जब तक है जान में थे क्या? अच्छा, स्क्रीन शेयर किया था क्या? स्क्रीन भी शेयर कर लिया था. चलो, मैंने नहीं डाला है, so we'll assume that उन्होंने नहीं किया फिल्म साथ में, ठीक है? Because I didn't know कि जब तक है जान में ऋषि जी भी थे, ठीक है? Okay, cool. What about I don't remember who was the next judge. Let's say Deepika and Amitabh Bachchan. Piku. Okay, nice. ठीक है. What about say Amitabh Bachchan and Joey Chawla? Bhootnath, correct. Juhi and Katrina? No, I also don't think so. As far as we know, no. So we'll let that be. Let's just go from Rishi ji now. So Rishi Kapoor and Juhi Chawla? बोल रहा था बोल. वाह, okay, ठीक है, सही जवाब. बोल रहा था बोल. What about Rishi and Katrina? अरे जब तक है जान में बहुत सारे लोगों ने काम कर लिया फिर. But I think they've also done Namaste London, I guess, नहीं? Namaste London, so that's what I had in mind. But okay, right. Rishi and Amitabh. Amar Akbar Anthony. 102 not out. Right, 201 combined age हो सकता है, but 102 not out. ठीक है. All right, great. So we have like built this nice graph. You can think of this as a collaboration graph if you want to give it a fancy name, but we kind of know what's the information that it's depicting for us. Now here's like our first puzzle. What we want to do is we want to take a walk on this graph. What does that mean? You want to go along the edges, okay? But the rule is that you're not allowed to repeat any edges and you're not allowed to skip any edges. So you want to visit every edge exactly once, yeah? So, and also you can just say, okay, I will take the edge 6 and then I will take the edge 1, right? That doesn't work. So if you take the edge 6, that means you're going from Juhi to Amitabh, and then the next edge must be going out of Amitabh, okay? You cannot you cannot do like edges that are completely disconnected from each other. Okay. All right, so the rules clear. So we want to take a walk starting at Juhi ji, and just try to, feel free to use pen and paper. There seem to be some blank sheets of paper for anybody who needs them. But just take a walk. Are the labels visible? Like you can make out which edge is which, right? I've color coded the edges just so you know. Like 3 is this horizontal edge, 5 is the vertical edge. So just take a walk, make sure to visit every edge exactly once. And what I want you to tell me at the end is, where do you end up stopping? Okay. Deepika. Okay. Okay, so let's wait for everybody to finish and अपना थोड़ा सा carefully check कर लो. I think आप दीपिका से थोड़ा सा distract हो गए मेरे हिसाब से. दीपिका पे stop करना थोड़ा मुश्किल है. As far as I remember, if I've set this up correctly. अरे okay, maybe somebody give me a sample sequence. आप दीपिका भाई साहब बताओ कहाँ पे रुके, मतलब क्या sequence? Do you have it written down or should I?
7, 8, 3, 4, 5.
लेकिन सभी edges visit करने हैं ना, 1, 2 ये सब छूट गया. It's not enough to visit all the nodes. You have to visit all the edges. So your sequence should have length 9. ठीक है? You can start with 6 or 7 or 2. You have to start with an edge incident on Juhi ji. So start your walk at Juhi, and so therefore feel free to use any edge that is incident on that vertex. ठीक है? Any edge going out of Juhi is fine. You have to repeat the nodes, है ना? Because if I ask you कि you have to visit 2 and 6 and 7, तब तो you'll have to come back to that node that many times. तो nodes तो repeat करना पड़ेगा. Nodes repeating vertices is fine. You cannot repeat edges. ठीक है? Okay, that's a possibility. Let me just wait for a few more people to finish, and we'll ask everyone to share their answers together. Okay. And there may be multiple ways of doing this. Okay, there's not necessarily a unique way of doing it. Okay. So where are you stopping? Oh, you're stopping at Katrina. Okay, that's another.
I also stopped at Katrina.
अच्छा ठीक है. जो लोग कैटरीना पे रुक रहे हैं अपना सीक्वेंस बताओ. Okay, you went from 6, 6, 4, 1, 1 से 2 कैसे हुआ? अरे 1 शाहरुख से निकल के फिर दीपिका पहुंच गए ना, तो फिर दीपिका से ही निकलना है. ठीक है, मतलब एच दीपिका वाले नोट से निकलना है, कहने का मतलब है. हाँ बताओ. Okay, everyone who has completed their walks, where are you stopping? Starting at Juhi. Starting at Juhi and stopping at Rishi Kapoor. Everyone stopping at Rishi Kapoor? Anybody managed to stop anywhere else? Okay, thank you. Yeah, as much as I would love to, she's my favorite actress, but yeah, try it, batao. You have to start at Juhi, though that's a constraint. Rishi Kapoor, okay. I made these slides before you guys work this out, and I'm also stopping at Rishi Kapoor. It's kind of on the slides. So, can somebody explain this phenomenon that when you start with Juhi, you stop with Rishi? Batao. Right, excellent. Yeah, perfect. Yeah. इसलिए हमने वो ऋषि कपूर और शाहरुख खान का कोलैबोरेशन भी मिटा दिया इस चक्कर में, टू मेक श्योर दैट देयर आर एग्जैक्टली टू वर्टिसेस दैट हैव एन ऑड नंबर ऑफ एजेस. सो दैट्स अ वेरी गुड ऑब्जर्वेशन, एंड इंडीड दैट इज व्हाट इज ड्राइविंग दिस phenomenon. And the theory is not much more than that really. So think about any sequence that must visit every edge exactly once. Now the sequence is about edges, but think of it from the perspective of the vertices, right? So suppose you have such a sequence. Think about it from the point of view of a vertex. So if you are sitting, let's say at the node representing Katrina, right? The sequence must visit this node and then it must also get out of this node, right? So every time you come in must be paired with, a node that gets out of that node, right? Unless you are at the start or at the end. Okay, if you are the node that is the starting node or the finishing node, then there will be, for the starting node there will be one node that gets out for which you don't pair it with a node that comes back, because you haven't come back to the node at the very end. And for the node at the end there will be an incoming node that you want, an incoming edge that you don't pair with an outgoing edge, because you just stopped there, you did not leave at the end. But except for those two nodes which are special, for every other node you cannot afford to have an imbalance in the number of times that you enter and the number of times that you exit. Okay, if you have an imbalance, then you were somehow stuck at that node, but that's not possible, right? Does that make sense? Jitni baar aaye utni baar gaye bhi. So if these were like locations in a city and these edges were representing roads, which is also something that graphs are often used for, the vertices represent locations, and the locations that are connected by a road have an edge between them. So imagine that you were walking around a city and you wanted to traverse, or you wanted to take every road exactly once. If you wanted to do that, then that's a very similar situation. So in fact the birth of the field of graph theory is often said to be connected with a gentleman who was sort of working with this puzzle. You may have heard of the bridges of Königsberg in Russia. So it's a city which has a few lakes and a few bridges connecting them, and he was wondering about whether you can visit every bridge exactly once. And it turns out that that configuration had so if you want the start and end vertices to be the same, actually every vertex must have even degree, but if they're different, then you must have exactly two vertices that have odd degree, where by the word degree I simply mean the number of edges that are incident on that vertex, right? So yeah, that's kind of the story here, and this is actually something called an Euler circuit. I think this condition is called Euler's condition for for having such a sequence. So you can set up this trick yourself, as long as you create a graph which has exactly two vertices that has odd degree, and you ask people to start at one of them and they are forced to end at the other. So as much as we love Deepika and Katrina, we are not going to stop there. We'll have to stop in this example. We'll have to stop at Rishiji. Okay?
Ma'am, is it similar to topological sorting?
Well, topological sorting is a related idea. For topological sort, you typically have directed edges, and I think you want a situation where you can line up everything and there are no back edges, right? So that is topological sort. I'm not sure if I'm not sure if you can, okay, so okay, I would say you're right, because you can only have, in a graph that does not have cycles, directed cycles, you can only have one source and one sink, I think. I hope I'm right about that. But yeah. Right. So in some sense, if you identify a source, you can force the sink or something like this. So yeah, of course there has to be some condition about the graph being connected, because otherwise you can just have a matching, like a collection of disjoint edges, and you can have multiple sources and sinks. Just want to be careful. So I think the question was about topological sorts, and that's so topological sort is something that applies to the so-called DAG. Okay, I'm messing this up, sorry. So that stands for, so the graphs are directed, which means that the edges, unlike in this example, the edges have orientations, and we will actually be seeing examples of directed graphs later. And acyclic means you don't have, you don't have a situation like this. This is an example of a cycle. And yeah, of course, the G still just stands for graphs. Okay, so so with directed acyclic graphs, what you can do is you can order the vertices in such a way that every edge is kind of going in just one direction. So this is, so one contrast with topological sort is what we are doing is a sequence of edges as opposed to a sequence of vertices. This is a sequence of vertices where, again, the vertices don't repeat. And again, I think what is true is that all the edges are oriented and they go in one way. What I am confident about is that you will have sources and sinks. When you have a directed acyclic graph. If you have a cycle, you may not have a source and a sink. Again, what do I mean by a source? It's a vertex from which every edge is just going out, it's pointing outwards, and a sink is a vertex where every edge is coming into it, right? So that's a source and a sink. So if you have a cycle like here, you may not have either a source or a sink. Every vertex is one edge coming in and one edge going out. It's kind of what we were experiencing when we were doing the Euler circuit as well. But on the other hand, if you have a directed acyclic graph, you can just, sort of start anywhere, and at some point you'll not be able to get out anymore. If you come back to where you started, you have a cycle, so it's not acyclic. So at some point you will get stuck, and the point that you get stuck, you can show is like you're getting stuck because all edges are coming in and you can't get out anymore. So, and a similar argument will show that you'll always have a source. So these vertices will exist. So those are sort of the similarities, but I can't draw a more direct connection with topological sorts at the moment. But it's a nice related concept. So thanks for that question. Cool. So let's try a slightly different trick. So I'm actually very sloppy with actual cards. So I thought I will code this up. This makes for a nice Python coding exercise as well. But because I wanted to show it to you here, this one's actually written in JavaScript. Some of you familiar with either the 21 card trick or the 27 card trick? Has anybody tried this? Okay. All right. So there's something called the magician's code, which is that if you know a magic trick, then you don't spoil it. So in case you've seen it, then please play along. But otherwise, I hope it's something new for hopefully most of you. So we'll need a volunteer that I can work with for this one. You just need to be able to remember a card for a minute or so. So that's all. No, nothing heavy. All right. So. And the yellow shirt for now, and then we'll go around. So pick a card and maybe tell somebody so we know that, maybe just write it down in your notebook or something. Pick a card that's visible on the screen, all right? Yeah, okay. So which row is the card in? Second. Okay. So at this point, this card could be like, okay, so to be fair, that question does tell me something about the card. It tells me that it could be any card in the second row. But okay, so let me just say that it's, I answer here, I say it's the second row. Now the cards got shuffled. Okay. They're shuffled pretty randomly. Where did your card end up now? Oh, really? It's not there? That should not happen. Okay, all right, thank God. Like, I just experienced a mild panic attack, but okay. Third row, okay, cool. Is that the correct card? Okay, cool. All right, does anybody else want to try? If you don't like, tukkabazi ho sakta hai. All right, so at the back, the lady at the back, yeah. Sorry, we're just trying to, yeah, cool. Thank you so much. Maybe we should hear him for, remembering the card throughout. Yeah, all right. And also for me for setting it up, but okay, go ahead, yeah. You picked a card? Did you write it down? Cool, all right. Which row is your card in? First row, all right, cool. What about now? This is like the scary bit, okay. Take your time. Still in the first row? Okay, cool. I changed a bit now. Where is it? Second? Okay. Ideally, I should be following along, but I'll just let the code do the work. What about now? Is that right? Okay, cool. All right, I survived that. Somebody else want to try? All right, cool. But again, prioritize going at the back. So let's refresh. Please pick a card and write it down. Oh, sorry. Yeah, I don't know if I triggered something by accident, but. Have you picked a card? You've written it down? Yeah. What row is it in? Second? Okay. What about now? Still in the second row? Okay. All right. What about now? First. Sure now? If you're not sure, the trick will not work. Okay. Like this is a magic trick that's driven by the audience. Ace of Hearts? Yeah, cool. All right. Yeah. Okay. Hopefully you believe me. It's not going to be like lucky 3 times in a row. But now I want you to tell me, how is this trick working? That's the puzzle part of the whole thing. Okay, let's do it slowly this time so that we can reveal the trick as we go along, and so hopefully you can perform it when you go back. So maybe once more, somebody wants to volunteer. Okay, the front. So pick a card and remember it. Yeah, which row is it in?
Second row.
Second row. Okay. Actually, let's just, sorry, maybe I'll do it in a way that, okay, so do you guys want to think for some more time, or do you want like a spoiler? Spoiler. Okay. All right. Okay. Hopefully this works. This has become a bit smaller. Let me see if. Yeah, should be better. You can see? Yeah. Okay. It's a different configuration. So maybe just pick a card again. Which row? Second. Okay. So you picked a card in the second row. So I know that it's one of those 9 cards. So when we redistribute the cards, and I said it's a random redistribution, that wasn't quite true. So it's not completely random. So what you do is you take the cards in the second row and you distribute them equally in the 3 rows when you place the cards next. Yeah, does that make sense? Yeah. And now when you tell me which row your card is in, it's not one of 9 cards anymore. It's one of 3 cards. Yeah, cool. So which row is your card in? Third. Okay, what will happen now? Yeah, the 3 cards get distributed again. And now when you tell me the row, it's uniquely determined. Yeah, so which row was your card in? Third again. So that's the 7 of clubs, I think. Yeah, cool. It is definitely more impressive if you just like actually perform this with actual cards, but it takes some practice for you to keep track of what's going on. But there's a variation on this called the 21 card trick. It's the same concept with a smaller number of cards, because then the way you lay out the cards, so if you catch me over coffee sometime, we can actually do it when like I'm less nervous and I can make mistakes. So we can actually perform it. So there you don't have to. Okay, so the 27 card trick, if you're performing it, you really have to create the impression that you're shuffling the cards completely randomly. Okay, otherwise, like the way I do it with my mom, I'm like very carefully taking this row and redistributing it. It doesn't work. So you have to like pick everything up quickly and just redistribute it, keeping in mind that you're doing what you need to do. But with the 21 card trick, there's really a fun way of memorizing how to do the redistribution, and it kind of works out magically. So there's a YouTube channel called Numberphile, and they have a feature on the 21 card trick. It's the same principle. Every question reveals more and more about the card in question, but it's accompanied with like a method that helps you do it quickly. So we'll talk about that offline. But this was the 27, the trick with the 27 cards. This how many of you have heard about binary searching? Okay, all right. So almost everybody has seen binary searching. So let's see if okay, my internet's not working here. I want to. Okay, so as I said, this is also a good exercise in Python if you want to actually implement it as sort of an interactive console program. I'll show you an example of something that we do that is kind of similar. But in the meantime, all right. So let's see if I can figure this out. Any questions so far about the trick with the 27 cards or the...
How are you learning Python in a browser?
Oh, this is, yeah, as I said, this is unfortunately, this is not quite Python. This is JavaScript. So you can sort of see the source right here. So this is fairly standard. You don't need any fancy JavaScript libraries for this. Like some of the project presentations I saw today were kind of scary. This is just pretty basic vanilla JavaScript. You just need a way to modify what is being displayed in a particular HTML container, do some calculations and redistribute things. So that's all that you need to do. But you can sort of do this also in Python, and you just need to, probably to make it attractive, you need to, know how to say print colored things to the console, and like, actual card shapes and stuff, and maybe even pictures. Yeah. Okay. Yeah. Yeah, that's a great question actually. So in fact, I was going to come to, let's see, let me do a similar trick, and you can, maybe that'll kind of answer your question. Let's see if this works. All right. Okay, having seen the 27 card trick, you might be able to reverse engineer this trick as well. It's a similar principle, but it's a number guessing game. Again, somebody wants to play along. It's more fun if somebody plays along. Okay, so think of a number, and let me know if you, so think of a number between 1 and 31. Okay, it doesn't have to be on the screen. Any number between 1 and 31, and tell me if you see the number right now. Yes? Okay. What about now? No? Okay, what about now? Okay. Next time I'll ask somebody to double check the answers, but okay. What about now? Do you see the number now? It's not there? Okay. And what about now? Yes? Okay, cool. Was your number 21? Okay, all right, that's why. Okay, let's carefully double check. So if you're doing 20, it's not there now, it's not there now, it's here now, it's not here now, and it's here now. Okay, all right, cool. Let's try this again with maybe, okay, all right, go for it. Is your number on the screen now? No. आराम से बताइए, ठीक है? Is your number on the screen now? It is? Okay. What about now? Pakka? Okay. What about now? Yes? Cool. What about now? Alright, 26? Okay. Very good. Okay. So how many questions are we asking? Did anybody keep track? We're asking 5 questions. And now remember, previously the answers were like one of 3 things, right? It could be row 1, row 2, or row 3. Now these are yes/no questions, right? So I am deriving in some sense a little less information, because previously what was happening is that with one answer I was eliminating 2/3 of the possibilities, right? But here with one answer, yes or no, I am only eliminating half of the search space, which might remind you of binary search. Okay, I'm in every step I'm eliminating half of the search space. So so the way these 5 screens were set up were essentially based on, I think, the bit value of the ith, ith most significant bit, or the ith least significant bit, depending on how you look at it. So the first, what's common about all the numbers that you're seeing right now? They're all odd numbers. So they're all numbers that end with a 1. So that's the least significant bit, right? The last one. So these are all the numbers whose last bit is a 1. And let's say we want to target 31 or something for simplicity. These are all those numbers for whom I believe the second last bit is a 1, I think. So that eliminates, so actually you can see some numbers here that I've already eliminated before. So if I was doing an explanation, I would not, to show how the search space is shrinking, I would not show you those numbers. But because we are still in performance mode, you see some numbers which I know that, they are not your number, but I still show them to you. Okay, so So if you were doing this with, I think if, let's say you're doing this with an unsuspecting cousin or something, you could do like 5 sheets of paper, and I think you can write down the corresponding power of 2 on them, like so 2, 4, 8 and so on, and every sheet on which your victim says that they can see that number, you just add up the powers of 2 corresponding to them. That's going to be their number. So that's one way if you wanted to execute this trick with actual pen and paper instead of doing it digitally, you can do it that way. Okay, it's fun. I think if your target is young enough, it's not obvious. It's not obvious how you're doing this to them. So I think it works well. So these are all those numbers where, so you're literally, with your yes, no answers, I'm literally reading off the binary representation of the number that you have in mind. So you're saying yes, no, and so on. So it's like 0, 1, 0, 1, etc. So if you're very good with bit arithmetic, you can probably just translate that quickly. I'm not, so I prefer just writing down the powers of 2 on the pieces of paper and adding them up, or to just cheat and write a JavaScript program that does all the heavy lifting. Okay, cool. So coming back to that question about can we do it with more cards? So I think when you're asking a question that eliminates 2/3 of the search space, at the last step, you want your search space to come down to 1 card. So reverse engineering from that, the last but 1 question, it has to be a question about 3 cards, so that the last question gives you the actual card. And then in the step before that, the best you can do is eliminate 2/3. So you have to come from 9 to 3. Right? And in the step before that, it's 27 to 9 by the same logic. So if you want to do more cards, you can do that. It's just you'll have to ask more questions. So I mean, and you'll have to reorganize, I think, what the table looks like and stuff like that. But you can, so the more you want to increase your search space, the more questions you'd ask. You can also try to experiment with making the questions more powerful. So usually I show the other demonstration first, because these questions are not they're not super revealing. These are yes no questions, so that's why even to distinguish between one of 32 possibilities, I actually need 5 questions instead of 3, right? So by making the questions more powerful, this is like saying I'm going from a binary representation to a ternary representation. So by making the questions more powerful, revealing more information, I could bring down the number of questions. But you have to be careful about how much you push this, because if you make your questions very powerful, then the charm of the trick is lost, right? So what's the ultimate question that you can ask? If you had to get an answer in 1 question, yeah, which one is your card? Right? That's the only question you can ask, right? It's a question with 27 possible answers. It's a very powerful question, but there's no magic anymore, right? So, I mean, you can ask, so you want to sort of strike a balance between how powerful your questions are and how many questions you want to ask them. So, if I ask them questions that don't reveal much, and you want to do it for like 100 cards, the trick will take half an hour to execute and people are bored by the end of it. So you have to kind of strike that balance. So 21 cards, 27 cards, 32 numbers, 64 numbers are like common doable combinations. That's what those kind of tend to be popular. So cool. All right. So so I think that's what I wanted to say about search-based card tricks. And now I'm just trying to think of what would be a good sequence to do the rest. So maybe let me see if. Okay, I need to figure out where I have. Okay, I had an embedded Python script on one of these slides, but I don't see it right now. Just give me a second. I'll just try to. Okay, so we can do this, we can try this a few times. I have a bunch of cards bundled up. Unfortunately, I happen to I happen to lose a couple of cards, so you might find some small inconsistencies in the actual trick, but hopefully you can live with that. So so this is a trick that needs to be handled with care, because again, you're all going to execute it. I'm the sloppy magician, so I'm going to rely on you to do it. So maybe we can again try doing this multiple times. So I will start here. So this will have to go back 5 rows. So what I want you to do is, you want to take this deck of cards and give it a cut. By a cut, I mean split it anywhere you want and put the top under the bottom, okay? But be careful to not shuffle it in any other way. It only respects this sort of very special shuffle. So give it a cut, okay, and pass it back and let them cut it as well. So I want it to get cut 5 times. And then from the back, what I want you to do is pick a card, keep it with you, and pass the deck. So pick not any card but the top card, okay? So because you've cut it so many times, it's kind of shuffled. Take the top card, and then we'll try to figure out what are the 5 cards that you have chosen, okay? That's what we'll try to do. Is the plan clear? Yeah? Okay. So I'm just wondering, should we do left to right? We don't have 5 columns, so we'll go backwards, yeah? All right. So start here, give it a cut, and pass it back for another cut. Okay, cool. So pick the top card. Don't show it to me. You pick the top card. All right. You can pick the top card. All right. You pick the top card. And you pick the top card. Okay. So now again, we are going to write a program that tries to figure out what those cards are. Okay. And I hope you guys don't mind standing for some time if required, those who are holding the cards. So if you have a red card, I want you to stand up. Okay. Oh, what? Okay. Okay, guys, the deck is it's a random deck. It's not only red cards, in case anybody is wondering, and it's not the same cards. I should have shown you that before. It's a genuine deck. We don't do cheap tricks here. We we're math people. Okay, so since it's all red, maybe you all sit down. Just it's okay. All right, so so I obviously don't have enough information, except that, it's one of some, it's 5 of some 26 cards, okay? 26, choose 5 big numbers. So there's no way that I'm going to, and you also change the sequence of the cards. So I really don't know from where you started picking the cards. So we're going to sort of, we're going to have, answer some questions in the hope of extracting, some information. All right. So, so these are random questions generated by the program. I'll ask you one and then I'll ask myself one. Okay. All right. So who picked the card here? You picked the card? You picked the card. So did you stay back for level up yesterday? Did you stay back for the dance program yesterday? Or did you attend the dance program yesterday? No. Okay. Do I cook? Okay. All right. Do sandwiches count? I think sandwiches should count, right? So I'm going to say, yeah, Maggie counts. I'm going to say yes. All right. Second row. Do you have a nickname? You have the card, right? So do you have a nickname as well? Okay. All right. What's your nickname? Okay. People call you Shreds. All right. So you have a nickname. Yes. Do I like horror movies? Okay. Yeah. This question is for me, so okay, I'll say yes. I mean, I haven't watched that many horror films, so I don't know what really counts, but okay, I'll say yes. Have you ever cheated at a game? Yes. Okay. All right. Is Spider-Man my favorite superhero? Okay, fine. I mean, there are some ties, but fine, close. Fourth question, in truth or dare, will you opt for truth? Truth? Yes? Okay. All cards are red, all answers are guesses, almost. You should have really stayed for the dance program, then it would be. Did you follow IPL? This question's for me, I think. Did I follow IPL this season? As a matter of fact, I watched a couple of matches, so yes. Last question, do you have an imaginary friend? No, okay. All right. Fine, that's like a tiebreaker. Have I ever broken a bone? Maybe. Yeah, if I stretch, like a tooth should count, right? I've like broken teeth. So let's see. Okay. Does anybody have 7 of hearts? Okay. 6 of hearts. 4 of hearts. 8 of hearts. And ace of diamonds. Yes? Did that work? Yes. Okay. It did. All right. All right. So. Alright, so I said we'll do this a few times. Unfortunately, there I cheated. I didn't really quite set this up so that it'll be fun to do multiple times. But we can try. Let's see. So I'll have to put them back in the same order that I did, I think. So you were the last to pick a card, right? Oh, bhai. Order. ठीक है. चलो एक बार तो काम किया, सब गवाह है. Everybody saw that it worked once. Yes? Okay, good. ठीक है. So now I'm like a little bit relaxed. If it doesn't work again, that's fine. So, okay, same story. Like cut this as many times as you want. This part I'm confident. I don't care. You can cut as many times as you want. So do we do this or do we do this? This call. Okay. All right. Let's see. We'll go around. Okay. ठीक है. So give it a cut and pass it back for another cut. A card afterwards. Yes, please. Your turn to pick a card comes at the end. Yeah. Cool. Okay, thank you. It was a careful cut. You can cut multiple times, but just carefully if you want. Yeah. Okay. Now I really don't know. Yeah, just pick a few and put it at the bottom. Yeah. I think it'll work the other way also, but take it. Pick the top card. All right. Yeah, pick the top card. Yeah. All right. So once again, for this program to do its telepathy thing, it needs it needs those of you who have red cards to please stand up. Okay, I think that's a lot better. Now the thing is, because I'm doing this a second time, I will confess that you will probably get some clues about how this works because of how we are doing it. So just watch carefully and maybe you can reverse engineer how this works. Okay, this is one of those tricks that's good for one time, but we'll do it again. All right, so did you attend? So please keep standing. I'm sorry, this time you'll have to keep standing. So did you attend Level Up yesterday? Okay. Do I cook? So this time sandwiches don't count. All right, do you have a nickname? Yes. Okay, cool. What's your nickname? Feel free. The program's listening, so. Okay, Devi, your first name. All right, cool. Do I like horror movies? I haven't watched that many, so I'll say no. Have you ever cheated at a game? All right. It doesn't ask me this question, unfortunately, but okay. Is Spider-Man my favorite superhero? It's a question for me. What did I say last time? I said yes. Huh? Okay, let's be honest about this. In Truth or Dare, do you opt for truth? Okay. I'm just like doing my calculations, might mess this up. Did I follow IPL this season? What did I say last time? Said I watched a couple of matches, so I'll stick to that. You have an imaginary friend at the back. Yeah. Okay. Have I ever broken a bone? We said maybe. I mean, I said I've broken a teeth. This time I'll say that's not good enough to have broken bones. So let's see. It's going to do the same thing. I should have made this a little more entertaining, but let's see. You guys keep standing through this part because it's important that it gets the right signals from you all. Okay, my 5 of spades was the card that was missing, so you may have a slightly different one. But do you have a 6 of clubs, any of you? Okay, all right. What about, do any of these cards tally? Because then we are probably off, like the sequence is off by a bit. Okay, so what are your cards? 7 of spades. Okay, so I think that's, okay, that's just gone down by, okay, so let me tell you, let me tell you more about how the sequence works. So, I mean, I think what has happened is, let me show you. Okay, as I said, it worked once, and this is not the best trick for multiple, so I thought we'll take our chances. Okay, it's fine. So here's what you can see. What you can see is the sequence of cards hard-coded in the program. Okay, so that's the sequence in which the cards originally were. So at some point there is a 7 of spades. So the first part of the trick is that if you cut the sequence, it doesn't really affect the sequence. It looks like you are shuffling, okay, but the relative order of the cards. So think of the sequence of cards being, you know, sort of a cycle. So let me maybe show you with, yeah. So let's say you have like this sequence and it's hard-coded into the program, right? And now if you cut this, if you think of this sequence as a cycle, so ace of spades followed by 2 of diamonds, followed by 5 of clubs, followed by 3 of spades, followed by, which deck did I give you? Did I give you the correct deck? Damn. Okay, so, all right, it's possible that it didn't work because I didn't give you the right subset of cards, but okay. Because okay, no, I think this is the rest of the deck, so this should be fine. Okay, so, right, so anyways, so the point is you start with these cards and you kind of just go around, like if you've done circular lists and things like that, it's kind of like that, okay? So you just cycle around. So when I ask you to shuffle by cutting, okay, this relative order does not change. Does that make sense? Yeah? So in some sense, you're really dealing with the same sequence of cards throughout, okay? And this was a deck of 32 cards, and we'll come back to why that's relevant. But I've essentially just repeated the sequence of 32 cards, so that's how it remembers the cyclicity. So what it's trying to tap into is like the first card that somebody picked, and it'll just give you the next 5 after that. So obviously, I think it did not start at the right place. Once the starting point is off, the rest of it is going off. So I'm sorry about that. This is a bit of a bummer, but since it worked once, I hope all of you are still curious about how it works. Yes? Yes? Okay, cool. And when you make it work, you practice a little more than me, okay? So, but all right, cool. So let's think about this together, because this is kind of like one of the main pieces that I want to tell you. Think about like what information did you give me apart. Okay, so now you know that the cards were rigged to some extent, like it was a particular sequence that I put them in, and we want to think about why that sequence was special. What properties does the sequence need to have for this trick to work? So let's think about it, and let's take our time thinking about it. What other information did you give me apart from what I already had from the sequencing of the cards?
I think it was in your answers. Each time you answered a yes, it was corresponding to a person who had a red card.
Yes, that's a great observation, very observant. So every time somebody was standing, the answer corresponding to, like, so we both got a question. So the question addressed to you was a throwaway question. The question addressed to me was the one that I control the answers to. So I would answer yes if you had a red card, and I would answer no if you had a black one. Okay, so that's how I'm transforming the signals in the room to the to the machine. Yeah. So now effectively the program knows. What does the program know at this point? It knows, like you said, the red-black sequence, right? So let's see if. Okay, I haven't used this much, but okay. So in this example, we had, I think, I said probably no, no, yes, yes, no. So once again, we have like a, you can think of it as a bit string, right? And how many possible bit strings can you have? Again, if you have 5 people, 32, just like with the other trick. This is just slightly like more moving parts to this trick is all. So you have 32 possible sequences. There's 32 possible pieces of information that I can convey to the program based on my answers, right? There are of course different ways that you can execute this, but this is one, like the question answer thing is one way of doing it. I think if you have better memory than mine, you can just like see who have the red cards and actually immediately come to the sequence if you remember exactly what the sequence is. But I'm getting ahead of myself. What's the point of the fact that there are 32 possible pieces of information that you are conveying to me through your answers? The point is that there are 32 cards in this deck. This is not a full deck. There are 32 cards here. So each possible sequence conveys to me in some sense the starting point of the card that I'm looking for, and after that it's just the sequence from there, right? So what do you need from the sequence? Will it work with any sequence? So for example, let's say let's do it with maybe a smaller number of questions and answers. So let's say we were just doing it with 3 questions, then I could do this with a deck of 8 cards. Okay, so what would I need from that deck of 8 cards? So for instance, suppose I had, let's say, ace of hearts, ace of diamonds, ace of spades, and ace of clubs. And let's say 1 of hearts, 1 of diamonds, 1 of spades, and 1 of clubs, right? So these are sorry, I meant 2 throughout, sorry. I could make that 10, but all right, so 2. All right. Cool. So, so what's my sequence from here if I were to translate it into the sort of the binary language? Let's say this is 1 1 0 0 1 1 0 0. Okay, and so 3 questions. So suppose you happen to pick the deck from here, then I get 0 1 1. So is this a good sequence to set up my deck with? What do you think? So what property do I need from the sequence? I need that no matter what combination of answers I get, in the sense, no matter what combination of red and blue I get from you guys, I should be able to pinpoint a unique place in the sequence that gives me that combination of answers, right? So for example, so what are the answers I can get? Because this is not in my control. This is genuinely like anything. You could start picking the cards from anywhere. All I know is that you're picking 3 contiguous cards from this sequence, but it could be any 3. So when I ask all the people with red cards to stand up, it could be that nobody stands up. It could be that everybody stands up like you guys did, right? And or it could be 001, could be 010, 100, or the other way 110, 101 and 011, right? These are the 8 possible sequences, and there are 8 possible start locations here. So for example, if all of you said okay, so 000 doesn't really feature anywhere in the sequence, right? Which means, so that's okay, but the problem is that means that some sequence must be featuring twice, because there are 8 sequences of length 3 hidden in this, right? So there are 8 starting points. Yes. So for example, 011, the one that I've highlighted, also shows up if the way you had broken the deck was at the 2 of clubs, right? So that would be 011 going around. Okay, which means that if you told me that, well, 2 of us have these red cards, the first person said I have a black card, the other 2 said I have red cards, I have no way of knowing if it was ace of clubs, 2 of hearts and 2 of diamonds, or was it the 2 of clubs, ace of hearts and ace of diamonds. Could have been either of the 2, right? Does that make sense? Which means that there is some ambiguity, right? So we need to resolve this by coming up with a better sequence, a sequence that does not have these repeating sort of, repeating subsequences. Okay, for those of you who have attended the workshops yesterday, is there like a break at the 1 hour point? No? Okay, cool. Alright, so then let's maybe work a break into the material by saying that let's spend a few minutes trying to come up with such a sequence. So these sequences actually have a name and they show up in all kinds of places in computer science, but also magic, which is cool, right? So so try to come up with a sequence. It could, I mean, if you're really like feeling like up to it, then you could try to do it with 32 cards, which means you need one of each of the 5 length bit strings to show up exactly once, right? But as like, I think what is a doable exercise is to try and make it work with 3. Yeah, exactly. So 8 cards, bit strings of length 3. So can you either come up with one sequence by trial and error, and you can report your sequences to me. I'll be happy to write it out and verify them, or try to see if you can come up with an algorithm that produces such sequences. That's a more general question. Cool. So let's maybe spend a few minutes doing that. Feel free to just, take a breather, and yeah, hopefully that works out as a break as well. Does the question make sense? Like, let me know if the question's not clear. But it's not completely clear. Okay. So what you need is, okay, so let's just do it in terms of bit strings, because that's actually enough. Because once you give me a bit string, I can find cards of the right colors to fit into it. Okay. So here's what we need. All right, so just as an example, if you presented this bit string 4 zeros followed by 4 ones, then these are the bit strings that are there as subsequences. But I think 101 and 010 are missing. You won't find that in this bit string. Okay, so if you take this bit string of length 8, right, then these are the guys that are missing. You'll not find any contiguous subsequence which is 010 or which is 101. 110 is by a wraparound. So if you go 110, you'll find it there. And similarly, 100 also comes from there. Okay, so think of this string really written around a circle or something. Okay, so do you want to read out your sequence? And we can try it out. Okay. 000 11101. Okay, so let's just double check that everything's in fact there. So sorry, let me write this down in red to distinguish. Okay, so 0, 0, 0 is there. 0, 0, 1 is also there. 0, 1, 0 is by a wraparound, yeah, okay. And 1, 0, 0 from the end. 0, 1, 1 is fine. 1, 0, 1 is fine. 1, 1, 0 and 1, 1, 1 is right here. Cool. Everything is there. We should say congratulations for coming up with that. You can now use the sequence to drive a trick with 8 cards and 3 questions. Okay. Instead of 0, 0, 0, 1, 1, 1, 0, 1, you'll have to find 3 black cards followed by any 2 red cards, any 3 red cards actually. So let's say red is 1 and black is 0. So this is such a sequence. You may want to do it in a way that makes the cards a little bit nicer. So in fact, it's a good exercise to find a mnemonically convenient version of this trick. But if you basically work with these cards, then basically if somebody says, for example, so let's say after we do all the drama that we did, okay, and then you end up with, let's say, 2 of hearts and 2 of spades and 5 of diamonds, right? So that's going to be, so when I ask the people with red cards to stand up, the first and the last person will stand up, and the person in the middle has a black card, so they're going to remain seated. Okay, so that's these 3 cards, but you don't know what these 3 cards are. All you know is that the pattern of the colors is 1, 0, 1, right? That's what you know it is. But you know that 1, 0, 1 is in the sequence, and importantly, it's in the sequence in exactly one place. Okay, yeah, and how do you know that it's in exactly one place? That's because you know that every subsequence is showing up, so you don't have enough space for any sequence to repeat, right? Because there's only 8 legitimate starting points, right? So you know, if every sequence is there, then no sequence is repeating, right? So you know there's 1, 0, 1, and you know that that's exactly in one place. That's going to be the last 3 cards. So if you remember in the sequence that you started with what those last 3 cards were by just committing them to memory, then you can just read it out like that. Otherwise, you can do what I did, which is to write a program that will identify it for you. Okay, so also I think if you're a bit clever, you can set up the cards in such a way that the patterns are convenient to remember. Okay, so you can think about like that's, I think, a good homework thing to do. But okay, so I don't know, do you have any insights on how you came up with the sequence? Hidden trial. Okay. Does anybody have any other thoughts on how to come up with such sequences? You can see that this is useful. And again, another interesting question is like, is this the only sequence with 8 cards that has this, with 8 bits that has this property? If not, clearly there are sequences that don't have this property. So how many sequences have this property and how many don't? There's like a lot of fun questions that you could explore based on that. But does anybody want to then try this for, you know, bit strings of length 16, which can give you, you know, answers to 4 questions if you want to level up your card game a little bit. You don't have to bother for 5 because I know one sequence and I'm happy to share it with you. That's the one in the code. But does anybody want to come up with one for when you have 4? So have you come across like greedy methods and algorithms? Like, has anybody seen greedy algorithms? Which is like, essentially, if you haven't seen them, that's essentially saying like, do the locally optimal thing. That's kind of the spirit, right? So suppose you're trying to build such a bit string. What would be like a natural greedy way of doing it, for example? So just maybe think about that. That's one hint. The other slightly more obscure hint is to, like, the reason I picked this was so that I could tie it back to what we started with, which was Eulerian circuits. So there's a very nice connection with Eulerian circuits. So we'll, you know, kind of talk about that. So if you can relate it to graphs somehow, you might find some luck there. So that's again a little bit vague, but that's another kind of hint. Okay, was there a question at the back, or like I thought somebody raised a hand, but no? Cool. So just so we're on the same page, what we're trying to do is now level up and come up with a string of length 16 that accounts for all sequences, subsequences of length 4. And I think you could continue doing it by experimentation and that would be fine, but maybe also think about whether there's like a systematic approach to sort of producing such sequences. Okay, overlapping is, yeah, I think it's kind of in the right spirit. So what do you mean by overlapping?
First,
Oh, sorry. Okay.
in the first one,
Uh-huh.
in case of 0, there is 0, 0, 0.
Mm-hmm.
And in number 1 place, it's 0, 0, 1.
Mm-hmm.
So two zeros are overlapping.
Yeah,
So
yeah.
we can go like 0, 0, 0, 1.
Right.
Then we see that another one is 0, 1, 0. So that overlaps with the last two digits of the 4 sequence that I just gave.
Okay,
so we
right.
overlap that. But like that, we can find this. We can take two at a time.
Mm-hmm.
See where they're overlapping.
Okay.
Then take another one. See where
Okay.
it's overlapping.
All right.
We can find.
I see. Yeah. Yeah. That's okay. So that's very interesting. I think there's elements of overlapping in both of the approaches that I mentioned, but I think what you're saying here is still slightly different. So you're saying you start with 0, 0, 0, which is the first thing you're looking for, and yeah, start with anyone. So might as well be 0, 0, 0. Like so, fine.
Then we could pick another one at random.
Well, it won't be completely at random because you already have 0, 0, right?
From the 7 ones that are left.
So now here, for example, the next one cannot be a 0 because then you're repeating. So here you're forced to put a 1, right? If you want, like, in fact, once you've committed that the first 3 should be 3 zeros, the fourth position can only be a 1 because otherwise you've already repeated and you have,
I'm saying that if
like,
the fourth one is starting with 0, I'm not putting in the fourth place. I'm just shifting the 0 under the last 0.
right.
Those two zeros overlap.
Right. So I think what you were kind of saying is suppose you take the next string, and I think of it as overlapping with this one. The thing is that then if I choose my next string to be 1, 1, 1, I will not be able to like squeeze an overlap, right? I mean that's not maximizing my space, right? I mean, okay, so yeah, I mean, if okay, so I guess people could also think of, I mean, of course, if you just take the concatenation of these strings, every string will be there, but you'll also have a lot of other stuff, and it's not useful because we really don't want repetitions, because repetitions means ambiguity and we'll not be able to resolve what cards there are, right? So you don't want repetitions. So now my only sort of, I mean, I don't know, maybe it's like a slight concern would be that suppose we were going through the list arbitrarily, right? So, let me reproduce the list here. It's probably not the best way to write it, but okay. So now we start arbitrarily. So we start with, this is what we are doing currently. We have the first thing we start with is 0, 0, 0. That means this is taken care of. Now the next substring is going to start here. So we already have seen 0, 0. So the nicest string to overlap it with is 0, 0, 1, right? Because that gives you the most benefit. If I try to push something like 0, 1, 0, 0, 1, 0 and 0, 0, 0 only overlap at one bit. And if I overlap it with something like 1, 1, 1, that's even worse because they don't overlap at all. So those are not nice next strings to go to, right? So in some sense, and if you really think about what could the fourth bit be here, there's really only one choice, right? Because like a 1 at this point is kind of forced, okay? What could you do next? So there are two possibilities, so let's try both. So you could do 0, 0, 0, 1, 0, or you could do 0, 0, 0, 1, 1. In both cases, if you think of it like you were saying with the overlap, so I have a 0, 1, and with a 0, 1 I have, so by the way, I should remember that 0, 0, 1 is taken care of, and with a 0, 1 I have sort of both of these possibilities, right? So at this point, both of these choices seem like they're legitimate. We may go on and get stuck a little bit later. I'm not sure. So, but at this point, there's no reason to pick one over the other, right? So in this case, what you're saying is you'll do it arbitrarily, right? Okay. So just to complete this algorithm, maybe we could so we're still doing it for 3. So let's say we go with 0, 1, 0, for example. Now you have now you've taken care of 0, 1, 0, and now you have a 1, 0, and again both choices are reasonable, right? Because I need a 1, 0, 1 and I also need a 1, 0, 0. Neither of those are done, right? So I can probably append a 0 here, and that should be fine. But now notice that we are kind of, what would you say? Are we stuck? We're kind of stuck, right? Because at this point, if I put either a 0 or a 1, I'm looking at strings that I have seen before, right? But on the other hand, maybe so we can backtrack a bit and sort of not do that, because we know that's going to lead us to a situation where we get stuck. So we prioritize the 1, 0, 1. And now we have 0, 1, 1 should still be okay. And now we have a 1, 1. I should do another 1 here. So now I have 1, 1. So have I already run out? I think I've already run out, right? I've run out of space. So I just have to hope that I get a 1, 1, 0 and a 1, 0, 0. So I think this accounts for everything. Yeah? Okay, cool. All right, so that was I would say, a reasonably systematic way of building it out. What we did was that we kind of pushed it, making arbitrary choices when we needed to. When we got forced, we basically did whatever we were forced to do. When we got stuck, we sort of backtracked and said, okay, maybe like we do in Sudoku, like you do something and then if you get stuck, you're like, okay, probably made a mistake, so you backtrack. Okay, but here's something that again, in the interest of time, I'll kind of leave it as sort of more of an exercise. But what you can do is actually always prioritize a 1 unless you are stuck. Let me just make sure. So let's start with 0, 0, 0 like we did. And whenever you have a choice, if you're forced, you're forced. But if you have a choice, just by default prioritize a 1. Okay. So that's something that you can check that it'll work when k is equal to I guess 2, because I said strings of length 2 to the k. So k equals 3 is what we are looking at. Sorry. So I mean, if you execute it here, which is, I think it's kind of close to what we did, except actually, why don't we just do it? So here we were stuck. Now after a 0, 1, so we know that we shouldn't repeat anything, so we want to keep track of what we have already seen. So at this point we have seen all zeros, we've seen 0, 0, 1. Now at this point 0, 1, 0 would be new and 0, 1, 1 would also be new, so I'll prioritize the 1. Now 1, 1, 1 is also okay, right, because 1, 1, 1 is also new. Now can I do 1? Yeah, I cannot do 1, 1, 1 again. So at this point 0, right, so 0 is forced. So I get a 1, 1, 0 out of it. And I can do a 1 now. Yeah, so sorry, have I run out of space? No, this is fine. So I get my, yeah, you're right. I get 1, 0, 1 and I get 100 as well, and I get 0, 1, 0 as well. Okay. So in this case, what we did was slightly different from before. We didn't do the get stuck and backtrack piece. What we did was, whenever we had a choice, we prioritized the 1. Okay. And if we were forced to put a 0, we would just put a 0. Okay. So if we didn't have a choice, or if you had to choose 1, it'll be 1. When you don't have a choice, you do whatever you're forced to do. So that's an algorithm. That's an algorithm for producing a sequence. It's an efficient algorithm, right? Because, well, it's efficient in the sense that, okay, if you had to implement it in your favorite language, what would you have to do? You start off with, if you had to do it for strings of length k, you would start off with all zeros, and from the k plus, like you would start off with k zeros, and from the k plus 1th position, what you would need is a way of checking if a particular string is on your list already or not, right? So you want to extend it by putting a 1, but at some point you cannot, like you have to check if putting a 1 is dangerous, right? Because if putting a 1 is dangerous, you want to put a 0. Right? So you have to check if after putting a 1, that string that you get from the last k bits, does that, like, is that something that has already occurred before or not, right? So at least at for a first level of implementation, you could maintain the set of strings that you've already seen in a dictionary or a list or something like that, and just simply check if, you know, if the string that you would construct if you added a 1, if it already belongs. If it already belongs, then you add a 0. If it does not belong, then you add a 1, right? So the outer for loop will run in time that's proportional to the length of the string that you're trying to build, right? Minus k, that's how many iterations it will need. But inside the loop, every time you're checking if something already belongs to a list or not. So that's again, so it's like overall quadratic in the length of the string that you're trying to build, because your list will also have that many elements. Okay, is that kind of clear, the roadmap for how to implement it? I mean, and it's quadratic in the length of the list. So you can think about ways of possibly making it more efficient, but that's not our focus for now. What we haven't argued is that the algorithm will, actually give you a string of the desired length. That's not obvious, right? It's possible that you just get stuck before, your string reaches length 16. That might happen. And when you do reach length 16 or length 32 or length 8 or whatever it is, then you know that you're in business, because the way you built the string, you were always creating a thing that you have not seen before, right? So you have no redundancies, and by a counting argument, you can show that if the algorithm goes all the way, then it actually gives you what you want. But it's not obvious that the algorithm does go all the way. So that's another nice exercise to think about, why will this algorithm never get stuck? At no point like 0 bhi nahi dal sakte, 1 bhi nahi dal sakte because we made some stupid choices before. That never happens. This algorithm always works. I think it was first shown to work like by hand for some small values of k, but then later somebody actually proved that it's always going to work, which I think is pretty cool. It's a very natural sort of an algorithm, but okay. All right, so let me just go back to this overlapping idea, and I promise that I will connect this with graphs a little bit, so let me try and do that. So the overlapping idea is exactly what you said. When you have 2 bit strings and they have like the tail of one is common with the head of the other, right, then it's natural to think about overlapping them to get a combined bit string. And this is like the maximum overlap you can have. If you smash it anymore, then it's the same string, right? So the maximum overlap you can have between 2 bit strings of length k is k minus 1. And when you overlap them, you then get a string of length k plus 1. Okay, fair? 2 bit strings of length k and you overlap them. So the first bit string of length k overlaps on its last k minus 1 bits, and then there's one more sticking out on the other side. So the length of the total overlapped string is k minus 1. Make sense? Yeah? Cool. Sorry, k plus 1. K plus 1. Yeah. What did I say? Yeah, k plus 1. Yeah, cool. All right, so that's how we got this string. So let's continue with this example where we are looking at k equals 3, because the graph would have been too big for k equals 5. So I'm just going to look at k equals 3. So here is a graph which has all bit strings of length 2, right? Because I want to overlap them and create strings of length 3. So what kind of edges do you want to put in this graph? Given what we are discussing how to create these sequences that have this nice property. Directional edges, yes, that's correct. And it might eventually create cycles, that's true. But here's like a simple question. Like you have like 2 nodes in this graph. Like when do I want to put an edge from here to there? When there's overlap, and when there's like this maximum kind of overlap, okay? Like not some chindi overlap. You wanted to overlap fully to create like a bit string of the next length, okay? Just the next length, because if they overlap like just a little bit, then you create like this big bit string, which is not useful for me, right? So for example, oops. Okay, so so I'm labeling the edges with the string that you get if you overlap the two endpoints of those edges in that order. Okay, so here if you overlap 0 1 with 1 0, then you get 0 1 0, right? And that's the label of that edge. So that's like the notation here. And if you overlap the other way, 1 0 with 0 1, then you get 1 0 1. Yeah, is that okay? And if you overlap 0 0 with 0 1, you get 0 0 1. If you overlap 0 0 with 1 0, I think that should be the other way, sorry. Yeah, 1 0 should overlap with 0 0 to give you 1 0 0. So this arrow should be pointing the other way. Sorry about that. 0 1 going to 1 1, I think that's in the correct order, and that will give you 0 1 1. And I think 1 1 should overlap with 1 0. Like, so that arrow, I'm not sure if it's pointing in the right direction. I think it is. So 1 1 overlaps with 1 0 to give you 1 1 0. Are there any overlaps that are missing? Like, do we have all the, like, how many bit strings do we have here? 6. How many do we need? 8. Okay, what are the missing bit strings? 0 0 0 and 1 1 1. Okay. Can we get them through overlaps? What overlaps? What strings overlap to give you 0 0 0? Self overlaps, right? So we need to add these self edges. 0 0 overlaps with itself to give you 0 0 0, and 1 1 overlaps with itself to give you 1 1 1. The other two strings are not, like, they're not self overlapping. If I try to overlap 0 1 with 0 1, there's nothing in common, right? So there are no self overlaps with the other two. But this is now the complete, the complete, I mean, it's not a complete graph, but this is the entire graph that I wanted to show you. Okay. Uh-huh.
Yeah, 0 0 0 1.
Sure. I mean, actually, I think we're going to come to like sequences of overlaps. So now, what happens if you can take a walk in this graph that visits every edge exactly once? What happens if you take a walk in this graph? Remember, we did this with Juhi and Shahrukh and all those people. But now instead we have 4 bit strings. So what if we take a walk in this graph that visits every edge exactly once? What can you get out of such a walk? So here, okay, so actually DFS will just like kind of keep going. I want to sort of also come back. So this is similar to a Eulerian walk more than a DFS, although like I'm sure a DFS would also be interesting to do here. I don't know what that gives you, but let's just take some walk here. Notice, remember what we said, for a walk to be successful, you need to have even degree, right? An even number of edges going out of every vertex, except for 2 if you're starting and stopping at different vertices. Okay. Now we'll have to modify this slightly because this is not an undirected graph anymore, right? It's a directed graph. So what's the natural way to adapt our statement? Like, instead of saying even number of edges incident on every vertex, what should we say instead? In degree should be equal to out degree, exactly. So the number of edges pointing towards you should be equal to the number of edges pointing away from you, right? So if that happens, then you have a walk that visits every vertex exactly, every edge exactly once, and actually comes back to the vertex that you started from, right? So now let's think about, maybe if you have pen and paper, why don't you just take a walk and see. You can start anywhere, you'll come back. Just make a note of the vertices. I'm sorry about like this edge. Let me just fix it because I think it can be confusing. So which edge was wrong? This one, right? So 1 0 goes into So when you're taking this walk, just make a note of the vertices that you're stopping at, like the vertices that you're visiting along the walk. you'll get back to the part that you start, right? And the fact that we chose these vertices to be bit strings of length k minus 1, and the fact that we put edges when there was like maximum overlap between them, can you get like, so can you get something interesting out of this walk, something that perhaps we are looking for? So how many edges and vertices does this walk have? Sorry? Right, but the vertices will repeat, right? You're taking a walk that visits every edge exactly once. So the vertices will repeat. So what's like the total number of vertices, including the repetitions?
You get the sequence.
You get the sequence that you're looking for. Okay, sorry? 8, yes, you're right. 8 edges and 8 vertices. Because it's a cycle, the number of edges is equal to the number of vertices. Make sense? Yeah? So, you get 8 edges and 8 vertices. Now, let's just think about, you're saying that you get the sequence out of it. So, I want to think about like, how do we get the sequence out of it? Does the path naturally, so remember we are looking for a sequence of length 8 that has all the 8 bit strings. The 8 bit strings are actually the labels of your edges, right? So if I just wrote down the labels of the bit strings on the vertices one after the other, then I would get a string of length. If I just wrote it, if I concatenated these things, I would get, well, each vertex has 2 bits, so 16, yeah. So 16 is too long, but what can I do? Yeah, just push it in, right? So write it down and keep pushing, right? Just overlap. So every time you visit, so you're taking this walk. So I start at a vertex. So let's say I start at 0, 0. And in general, this could be k bits. That's fine. I start at 0, 0. I take one edge and go to the next vertex, and whatever I see, because this was a directed edge, I know these two things overlap, right? So I write down the next string and I push it back, right? I exploit the overlap. So the total length of my string increased by just one, because like you had k and you overlapped k minus 1 bit, so you have one new bit that you got to add, right? Now I take the next step, okay? I take the next step, then I go to another bit string, which is of length k again, but it overlaps with the previous one. So you again push it in and you're just adding one new bit, right? So if you have taken 8 steps, right, starting with wherever you started, actually after you start, I think it's just going to be 7. So you just add 7 more. I mean, in fact, I don't even think you need to, okay, if you actually take the walk, I think we'll be able to figure this out. But the idea is that, you know, you just keep pushing your overlaps, and notice that because every edge occurs exactly once, actually, okay, maybe I should say this more clearly. When you complete your walk, you come back to where you started, right? So that overhang that you get, you can just delete it, because that's going to be the wraparound that you get in the sequence, right? Remember, sequences have been wrapping around, right? So we take from the end, we take 1 more, we take 2 more from the beginning. So those are going to coincide because we stop at the place that we started. So we just drop that overhang. So actually our sequence will end up being of length 10, but you can drop the last 2 because the last 2 will be the same as the first 2. So you don't have to worry about it. Okay? Does that make sense? So you basically go around, and after you do all this circus, what do you actually end up with? What you actually end up with is a sequence that you're looking for, right? Why is that? Because every edge appears exactly once in this walk, and those edges correspond to subsequences of the sequence that you built, right? No, not even subsequence, actually substrings, like literal substrings of the sequence that you built, which is exactly what you were looking for, right? So, yeah. Mm-hmm.
0, 1, and 1, 0, 2, 1. Then we're just missing one on that edge 1, 1.
Okay, sorry, can you say that again? 0, 0?
0, 1.
Yeah.
1, 0.
Mm-hmm.
Then again we are going to 0, 0.
Right.
So aren't we missing that if we follow this path?
Okay. So what we need is, so okay, that's a good point. So not every walk will correspond to a sequence. It's only those walks which actually visit every edge exactly once, only those will correspond to. Yeah. So you need what we call these Eulerian circuits, right? You will need an Eulerian circuit. What you want is a walk that visits every edge exactly once, and you know that that's possible to do. Okay, so maybe I was a bit sloppy in the beginning. I said that if you have an Eulerian circuit, if you have a walk that visits every edge exactly once, it must be the case that every vertex has even degree. Except the start and end points, and if the start and end points are the same, then in fact every vertex must have even degree. And for directed graphs, instead of even degree, you say in degree is equal to out degree. Number of edges coming in equals number of edges going out. So this is, if you have a walk, this must definitely be true, right? Because if this is not true, then a walk will not be able to manage, right? If you have some vertex whose in degree is, let's say, more than the out degree, but you know that if there was a walk, every time you came in you had to go out, right? And edges don't repeat, so every time you came in it was through a different edge, every time you go out it's also through a different edge. So if in degree is more than out degree, there will be a problem. But what I did not tell you is that if this is true, that the in degree is equal to the out degree for every vertex, you will also have such a walk that visits every edge exactly once and starts and finishes at the same vertex. So that is what we are using. We are using the fact that because, so let's argue, but before we do that, I think there was a question. Sorry, yes.
I didn't understood this part, so like
Okay.
I'm just thinking in this way, like if I start at 0, 0 corner
Mhm.
and go anti-clockwise, I will reach to 0, 0, right, and I will cover all the corner points, right?
Let's see, can you actually share your walk? You go from 0, 0 to 0, 1.
And then 1, 1, and then 1, 0,
Okay.
and then back to 0, 0.
Right, and then okay, so that's again, that's not a walk that covers every edge exactly once. That is a valid walk in the graph, right? But what we are looking,
Can, I
Yeah.
didn't understood this part, that's what I'm asking. So can you show like one path?
Sure,
and
yeah.
Show how states get compressed. and
Sure, yeah, maybe let's just walk through the whole process. Yeah, that's a good point. Okay. I have no idea what triggered that. Okay, all right, cool. So maybe let's just draw this graph again quickly. I'm sorry, I really should have put this on the slides as well, but I think we can manage. So I said 0, 0, 0, 1, 0, 1, 1, 1, 1, 1, 1, 0, and 1, 0, 0, 0, and these guys. So is the construction of this graph clear? Does that make sense? Like, what are the vertices and what are the edges? So the vertex set or the nodes is like strings of length 2 to the k minus 1. Okay. So here k is equal to, sorry, I should say k minus 1, not 2 to the k minus 1. Sorry. So k is like the length, like the number of questions that we ask in the trick, right? It's the length of the chota sequence that we are looking for. 2 to the k is like the length of the bada sequence that we're looking for. So this is strings of length k minus 1, which is why when you go across an edge, you get like, you do the overlap thing and you get a string of length k. Okay, so these are the vertex sets. This is the vertex set of the vertices, and the edges is, okay, if you have a vertex v being represented by b1, b2 up to some bk minus 1, and u being represented by b prime 1, b prime 2 up to b prime k minus 1, then uv is an edge if and only if, what do we want? We want b1 prime to be equal to b2, right? We want to be able to push the overlap completely. So we want b1 prime to be equal to b2 and ta-da-da up to bk minus 2 prime being equal to bk minus 1. Is that correct? That way the b prime k minus 1 will overhang from this side and the b1 will overhang from that side. Everything else in between will overlap. Yeah. So that's the condition for putting an edge between two vertices. Sorry? Right, sorry. So that should be from, yeah, these are directed edges. That's a very good point. So you have an edge from V to U if you can push U into V, okay, in terms of overlap. So thanks for that. So that's correct. So, so actually before we take that walk in this graph, let's actually see if we can make sense of, like, is it true that the in degree of every vertex is equal to its out degree, right? So let's fix any vertex. Let's take V, and what is the okay, so what we want is, so these are bit strings, right? So what can V overlap, like what is that other string that it can have an edge to? Can it have an edge to like multiple bit strings? Is that possible? Because remember, the other bit string is constrained on its first, yeah, so there are only two possibilities, right? Because it's completely constrained, like the other bit string who wants to be friends with V, okay, who wants to have an out edge from V, is forced to match with V on like wo 36 gun hota hai na, so you have to match with V on like the last k minus 1 bits, okay, like yeah, for those who don't have the context, 36 gun is like the number of qualities that a prospective groom and a bride must match on for the match to actually work out. So it's kind of like that. So if you want to match V to U, they must tally on like V's last k minus 2 bits must be the same as U's first k minus 2 bits. So U's degree of freedom is only on that last bit, okay, and so the last bit has two possibilities. So if you look at this example, like 0 1, 0 1 can merge into 1 1 or 1 0. So those are the two out neighbors, okay. And what about the in neighbors? The in neighbors is a string that can merge into V, right? Correct? So the same thing in terms of if you look at in this example again, you look at 0 1, you have 0 0 coming into 0 1 and you have 1 0 coming to 0 1. So there it's the first bit that has that degree of freedom. For the other guy, the last k minus 2 bits must be the same as V's first k minus 2 bits. So the first guy, the first bit has some degree of freedom. So that's again going to be two people that are adjacent to V, okay. And sometimes when you toggle that first bit, you might get the same vertex. That's what's happening with 0 0, for example, right? So 0 0 has like is neighbors with itself, because when you take 0 0 and you say okay 0 and then the last bit can be a 0, that's again 0 0. So that's why you get that self edge. Okay, cool. So so a self edge will count both as an edge that's incoming and outgoing. Okay, so that cancels out right there, and other than that, it has one incoming and one outgoing edge. Same for 1 1. So we understand the structure of this graph. Every vertex has in degree equal to out degree equal to 2 with the correct interpretation of self edges. That's fine? Yeah. So the graph makes sense to everyone, the construction, these properties. So we know, although I haven't given you a proof yet, for now take it for granted that if every vertex is equal in degree and out degree, you can actually take this walk that visits every edge exactly once. So if you believe me on that, let's put it to the test. Hopefully we can find a walk that visits every edge exactly once. So like some of you were saying, maybe we can just do the sort of the outer round, which, so for instance, let's say we start at 0 0, and let me just finish off this edge by doing 0 0 again. Okay, so that's my first step. Then I want to go around the outer diamond sort of thing, but so I go to 0 0 0 1 0 1 1 1. Now let's finish off the self loop, because we may not have a chance to visit this edge again, right? So let's finish off the self loop here. Now from 1 1 we go to 1 0. Now before we come back to where we started, we should probably do that little detour to 0 1 and come back, okay? Because if we don't do it now, it's now or never, right? Yeah. So so let's go to 0 1, come back to 1 0, and then do the 0 0. Okay. All right. So this says, I think somebody had pointed out early on, this is a sequence with actually 9. I don't know if I should be counting that 0 0 again, but that's, I mean, it's really a cycle. So I'm going to put that edge there and not write this again. Everybody comfortable with that? That's really the sequence. Okay, so that's the cycle that visits every edge exactly once, and of course it's going to repeat some vertices. Now if we were to concatenate these edges, I mean, so how do we get the sequence out of this? What we're going to do is we're going to write these down, but because we always went across edges, we should be able to exploit the overlap, right? So let's do that. So when I write, we're going from 0 0 to 0 0. That's just one extra string there. So notice that this, if we just wrote down, if we just wrote down the bit strings one after the other, it would be 16. It would be a sequence of length 16. But now because we are going to just, crush the overlaps, it's going to become a string of length 8. Okay. So, so please correct me if I'm making mistakes here. So we'll start with 0 0. That's the first one. The second one is 0. Then the third one is going to be a 1 for the next bit. The fourth one is going to be a 1. Then another 1. Then a 0. Then a 1. And then a 0, right? And remember, it was possible to do this because we have been traveling along edges, okay? Because the edges were carefully put to make sure that this overlap is feasible, and we are doing it for k equals 3, but it's the exact same thing for any larger k, okay? All right, yeah.
There's an extra 0.
Oh, sorry, did I put an extra 0? Yeah. One 0 0 1. Oh, I think, yeah, that's probably correct. I didn't have to. Yeah, so let's, do we want to confirm that this string actually works? I don't know if it's the same as some string that we got before. 0 0 0 1 1 0 1. Somebody had said that, no? It's the same one, right? Yeah, 0 0 0 1 1 0 1. So we have checked this already. It's the same thing. So we know that every substring with 3 of length 3 actually appears exactly once. But so now is the process clear of going from the walk back to the string?
So we are crushing only one common digit.
In this example, it will be one common digit, right? If it was a bigger graph for say k is equal to 4, you would be crushing 2 common digits. For k equals 5, you'll be crushing 3 common digits. So, yeah, k minus 2 always, yeah. So 2 strings of length 5, they overlap. Actually, they overlap on 4. So let's see. What did we do here? Okay, so for 5 length strings, if k was 5, we would be working with 4 length bit strings. So that's why you would be, the crushing would be for 3 common digits. You're right. So from the perspective of k, it's going to be k minus 2. Yes. Right. Yeah, so I mean it's really just a space constraint. In principle, it should be easy to replicate this exercise for the trick that we actually executed. You start with a graph on, I believe, 16 vertices, because you're now looking at strings of length 4 mashing into each other to give you strings of length 5 at a time. And then you would do that walk around that graph. So 16 times 2 would be 32. And then you kind of do the overlapping bit and you bring it down. Actually 16 times 4 would be whatever it is, but then the overlaps will take care of it and it'll give you a string of length 32 finally. So yeah, I'm not doing the arithmetic very well, but it works out in principle. Okay, so bigger graph, more vertices, more crushing, more action, but finally you will have your string of length 32 to execute your trick with. So just to recap everything that we have said, essentially you're looking for these strings that have these properties, which have these properties that the length of the string is exactly 2 to the k, and each of those 2 to the k bit strings of length k appear exactly once as a substring. So a bit string of length 2 to the k has 2 to the k starting points from beginning to end. When you reach the end, you kind of wrap around. And so you want each of those to give you a distinct substring. So clearly this is not going to happen with every bit string of this length. For the ones that it does happen, these strings are called special. I mean, these strings are special and they're called, I think, De Bruijn sequences. You can look them up. They have lots of applications. They come up in interesting ways. And as I said, a good question to think about is how many sequences have this property. So if you can take multiple walks around those graphs, you get different sequences, right? We also sort of came up with a greedy algorithm to produce the sequence. You can try to think about if there's any connection between the two approaches as well. But what do these sequences give us for our puzzle, which was the card trick? Once you have such a sequence, basically substitute every 0 with, let's say, a black card, and substitute every 1 with a red card. Okay, so line up 32 cards with that red and black sort of a pattern. You can pick your red and black cards however you like. Again, good exercise to think about. If you can pick them in such a way that makes it mnemonically easier, that, you know, if you see 0, 1, 0, you can sort of immediately figure out where did that pattern appear in the sequence of cards. So you want to go from basically the sequence of cards tells you how you can go from pattern, which is coarse information, it's just the red black information, to the full information about actually what cards there are. So this is like the math that's kind of driving the whole trick. So once you have that, again, you can execute the trick in multiple ways. The coolest thing is if you have like good memory, then you just remember the whole damn sequence. You remember what comes where, and then when the people with the red cards stand up, you can sort of immediately read the cards off. That's like the ultimate version. But like an amateur like me, well, you should still be able to do it at least once properly if you have something like this. So here, all that we are doing is essentially communicating to the program which were the red cards, and you know, so there's a little bit of drama that you do for that to happen. And then depending on you know, so that's just these answers that I gave, that's the bit string that we talked about, right? And from the bit string, for me it was just convenient to convert the bit string to an integer, and I know it's like the sequence from that point on, I need to report the next 5 cards. Yeah. All right. Does that all kind of make sense? Yeah. Okay. All right. Sorry.
Response from the user is not taken into account.
No, those are just throwaway questions. Yeah. You can like spice it up with more questions and more like, yeah. I mean, a lot of magic involves a lot of fluff. Okay, like a lot of stuff that you never use, but it's kind of there to distract, because when somebody's trying to reverse engineer the trick, like they, at least the first time, they won't know what's useful and what's not. But I think when we did it the second time, I think at least a couple of you said that I was answering yes every time somebody had a red card. So so that's again not completely ideal for yeah, for I guess multiple repeats, but I think it's very doable at least once. And if you're good with memory, then you don't rely on this. So then you can do it as many times as you want. Yeah. So unfortunately, I haven't done like my homework on. Again, I think it's a nice exercise to try and do it in a way that you can remember the sequence of cards well. So again, if you find me outside, you know, I can show you a couple of sources where there are ways of doing it more systematically. So yeah. That's not the approach I took here, but I'm happy to share it with you offline. So so I do have like a couple of more puzzles lined up, but they're not exactly 5-minute discussions. So let me just you know, maybe let me just open up the floor for questions. And you know, if you have any questions about the things we discussed, by the way, if you want to look this up, these are called self-working card tricks, or more boringly, math-based card tricks. And self-working card tricks are for people who don't know how to do like proper Beimani wala lead of hand and things like that. That's like professional card magic. But if that's something that you don't have the patience to practice, then you can do these self-working tricks, which are essentially driven by math and which are driven by sort of, you know, patterns in the cards. So the 21 card trick is an example of that. The De Bruijn sequences, these sequences actually like are the engine for more sophisticated card tricks as well. You can imagine that this gives you quite a bit of like quite a bit of sophistication, and you can play around with it. There's other like okay, so like I said, the De Bruijn sequence, one nice thing is that the cut, shuffle, does not affect the relative order, which is nice. So you can, I mean, again, if you practice a little bit, you can actually shuffle the cards doing repeated cuts and really make it look like, look like you're giving it a proper shuffle. You just have to be careful to not screw up the order. Like if the order is screwed up, the whole trick goes for a toss. But if you're good at this sort of just keep in mind that you don't mix the relative order and you do it reasonably fast, you can make it look like a proper shuffle. Other keywords that you can look up, and that's what I was going to talk about, but we are slightly out of time. So you can look up perfect shuffles and hammer shuffles. These are two more categories of shuffles, which again, I think it's cool to write some code to simulate these shuffles. So let me just tell you about like perfect shuffles. They're actually executable with some practice. A perfect shuffle is where you take a deck and you divide it into exactly 2 equal halves and you splice it up and you interleave them perfectly. So one card from the left, one card from the right, one card from the left, one card from the right. Okay, a lot of fun to watch on YouTube, like slow motion videos of people doing these perfect shuffles. But not only are they like perfect sort of in terms of how they look spectacular, of course, but mathematically they have a lot of interesting properties. So there's a lot of like a lot of properties that get interestingly preserved in spite of like this thing being a perfect shuffle. So that leads to some very impressive magic tricks, because when you do a perfect shuffle, your audience is like, ye to pura gaya. This is like, these cards have really gotten mixed up. But if you do the perfect shuffle perfectly, and you don't have two cards like stuck together or whatever, if it really perfectly does that, like if you manage to execute the interleave perfectly, then some very interesting parity based properties get preserved, and that can be the basis of some really cool and very convincing looking magic. Hammer shuffles are again more sort of cut based shuffles, and there are a few more things that you'll have to do, and again they preserve many interesting mostly again parity based. Usually hammer shuffles also involve cards being face up and face down. So most of these tricks, it really looks like something super random is happening, but you'll have properties like, oh, every card in an even position, if it's an even card it's face down, or if it's if it's a black card it's face up. You can preserve properties like that, all while doing these shuffles which actually preserve those properties. And then once you know these properties, you can actually make your own card tricks based on those. I mean, it's a lot of fun to think about it. So it's also like a great way of practicing your like discrete math combinatorics muscles. But at least I think it's pretty cool, and it makes for like a good evening with friends once you know all the math. So I think that's like one of the best motivations for learning math is to have it empower you to have a good time with people. So yeah, I mean, I hope I hope at least some of this was new for some of you. And once again, I really appreciate your sort of being here post lunch and after like a lot of events have already happened. So yeah, I mean, I think if you have any questions or comments, I'm happy to discuss now or even later. I'm sort of around. This would be a good time for, if there are a couple of quick questions. I can find a way of sharing like pointers to like all of the stuff is online. So I'm kind of working on doing like a short blog with pointers to different tricks that you can look up on. Like Numberphile has some really great videos that explains the math as well. So that would be a good place to go. So I'll see if I can find a way of getting those links across. Otherwise, you will, if you go to neeldhara.com, that's my website. So if you just look up the blog, then that'll, it should soon be like the first article there. So yeah, sorry, that's a bit sloppy, but yeah, that's. Well, actually, I mean, De Bruijn, so these are called De Bruijn sequences, for instance, have like applications in, I think, even error correcting codes and like vision, and like it has a lot of like serious applications, and it comes up all the time. In terms of games, so like if you're talking about mathematical games, yeah, I mean, these sorts of properties are definitely used across. So there's this whole field called So there's of course game theory, which is something that's more like what economists do, right? They think about strategy and they think about equilibria, and they often apply games in the context of markets, so there's money involved and things like that. But there's also like this cool field of math and CS that studies combinatorial games. So if you really have a game that you enjoy, like Go or poker or chess or any of these things, the people who actually study it for a living in terms of strategies and all kinds of combinatorial counting problems. Absolutely, yeah. There's, I think, a lot of exciting work in that sort of thing. Also, there's like, I think, very serious AI angle on games that people are very actively working on. So right now there's a lot of work happening in the space of like poker bots that can play, that can learn how to play poker well, estimate those probabilities well. There's of course a long history of chess playing bots, and Go has been in the news because of AlphaGo. So yeah, maybe this is not like that unrelated to like the hot stuff with AI and ML. I think a lot of interesting work in the AI space for game playing of this sort. Yeah, but that's not really what I touched upon. But if that's something that anybody is curious about, that space is extremely active right now. So cool. All right, I think it's just about 4, and you didn't even have a break. So thanks so much for being here. It was a lot of fun, and thanks for being such a sport. Thank you.